Hi, I'm Oliver, and I'll be talking about making interval arithmetic robust to overflow. This is joint work between the University of Washington, where I go to school as a PhD student, and the University of Utah, where Pavel Pancheha is a professor. So let's get right to it. The title of this talk is Making Interval Arithmetic Robust to Overflow, but what I would really like to call it is Movability Flags, Do Your Intervals Shrink at Higher Precisions? The problem with this title is that it doesn't make sense to anyone until you've already seen the talk. So for the rest of the talk, I'll be talking about our contribution, movability flags, and how they answer the question, do your intervals shrink at higher precisions? To motivate that question, I'll first introduce real computation, which is our target application for interval arithmetic. Then I'll introduce what interval arithmetic is and how it might answer this question. Finally, I'll talk about a problem that comes up in practice, which is overflow, and give the solution, which is movability flags. So a common question someone might want to ask would be something like this. What is pi times 4.6 plus 0.06? We might represent it as something like this. Pi is some infinite number of digits times 4.6 times 0.06. And your calculator very helpfully will tell you, well, I have no idea, because pi is not rational, so I can't compute this exactly for you. Well, maybe what you really wanted is this computation computed up to some number of digits. So your calculator may helpfully ask, how many digits of precision do you actually need? Here I've written this R2 operator, and I'm going to say that stands for rounding to two significant figures. And in this talk, we'll use significant figures as an analogy for floating point arithmetic. So maybe we actually just wanted 2 digits of precision. We wanted it correctly rounded to 2 digits. Well, it's still unclear how to calculate this, because pi is still irrational and we can't do the computation then round. So one thing you might try, and this is what lots of calculators do, is they round the intermediate computations before performing the operators. So here I've written that we're going to round pi first, before we do the multiply. And then we'll get 3.1 times 4.6. Doing the multiply, we get something like this. And again, we'll round the intermediate computation because we're only going to allow ourselves to use 2 significant figures of precision here. Rounding to 14 and doing the addition, we see that we're rounding 14.06, which is completely not the answer that we wanted. We see in the bubble that we wanted 15, and we're upset because we didn't get that answer. Well, maybe the problem was that we didn't use enough precision, so let's try again with a precision of 3. Right, would higher precision work? Let's try 3. So rounding pi to 3 digits of precision with 3 significant figures, we get 3.14 times 4.6. Doing the multiply, we get this, and rounding again, we get 14.4. And then rounding the added numbers, we get 14. So we still didn't get the right answer. And this is very concerning because we bumped the precision and we didn't get the right answer. But even if we did get the right answer, it turns out you do if you use 4 digits of precision, how would we know that we got the right answer? So the real question is, how much precision is enough to give us a good answer? And to answer this question, we're going to use interval arithmetic. So here's how interval arithmetic works. I'll give some background on that. Interval arithmetic is computing with intervals. So say you have some variables a and b, and you know the input ranges those variables could take. Well, now when you see a multiply, we're going to answer the question, what possible values could the multiplication take given these input intervals? And the answer in this case is that if you take the smaller of the endpoints for the inputs and the bigger for the endpoints of the inputs, then you get 2 new endpoints because we're trying to minimize the multiplication on the left and maximize the multiplication on the right. So the values that this computation can take are 0 to 4, because the lowest number we could get is 0 and the highest number we could get is 4 from 1 times 4. Alright, so that's interval arithmetic. We're going to have a bunch of operators that compute using intervals instead of numbers. So now, just for learning's sake, let's imagine that the input interval was smaller. Instead of 4 here, we had a 3. And let's do the calculation again. So substituting the intervals and doing a multiply, we get 0 to 1 times 2 to 3. And and then the 3 drops down, and so we get 0 to 2 times 1 to times 3. And the final interval will be 0 to 3. And so by shrinking the input interval, we've also shrinked the output interval, and that's what I want to get out of this example. So the idea is that in interval arithmetic, one nice guarantee you get is that if you shrink or make the input intervals smaller than they already were, the output interval can only get tighter, it won't get wider ever. So using that idea, we may be inspired to use interval arithmetic for real computation. So here's an expression pi times 4.6 times 0.06. And remember, before we couldn't calculate this because pi is irrational. So let's try to do it using intervals. Let's substitute all the numbers into intervals first. And I've written right here that the intervals will over-approximate the real computation. That is, the idea here is that we want our output interval to contain the true answer somewhere in it for the real computation. Since we can't actually compute that value itself, we'll over-approximate it by putting an interval around it. And so pi is not rational again, so this time we need to round. And the key here is that we want to round conservatively. So I've written the down arrow on this rounding operator to say that on the left endpoint we need to round pi down, and on the right endpoint we need to round pi up. And in this example again we'll use 3 significant figures of precision. So performing that rounding, we'll get an interval that's 3.14 to 3.15. And you can see that this interval captures pi inside of it, because 3.14 is a lower bound on pi and 3.15 is an upper bound. Next we'll perform the multiplication and do another intermediate rounding. So here we get 14.444 to 14.49, and doing another rounding we'll get this interval. Doing the addition and another rounding operation, we'll get 14.4 to 14.6. And the interesting thing here is that we know the true answer is between 14.4 to 14.6, but we don't know where in the interval it is. So if we rounded the answer, it could be either 14 or 15, because the true real computation could be 14.4, in which case it would round down to 14, or it could be 14.6, as high as 14.6, in which case it would round up to 15. So the cool thing about this is that the interval arithmetic has told us that 3 digits of precision was not enough. So we don't just get a wrong answer, we get that we need more precision to get a correct answer. So let's try this again with 4 digits of precision. Here we have the same thing, but we're going to round to 4 digits of precision. We'll get the interval 3.141 to 3.142. Doing the multiplication, we get these numbers, and doing the rounding again, we'll get tighter intervals this time, 14.44 to 14.46. And now doing the addition, we get 14.5 to 14.6, and luckily both endpoints round to 15, so we know that the true answer rounds to 15, and we get the guarantee that 15 is the correctly rounded real computation. So interval arithmetic has saved the day. Great. So this example suggests an algorithm for doing real computation, and the algorithm involves increasing the precision until we get an answer. So let's write down that algorithm as pseudocode. Here is a function called real compute. It takes a math expression, a input point, and a desired precision p. And so at the beginning of the algorithm, we'll set our working precision to p. And the working precision will be the precision that we're doing our interval arithmetic at. And now let's start a loop. And at each iteration of the loop, we'll perform interval arithmetic with this IEval function on the expression and input and the working precision. So we'll get 2 endpoints A and B out of that. Next, we're going to round each endpoint just as we did in the example. So the key here is that if both endpoints round to the same number at our precision p, then we've found our answer. The whole interval rounds to that number, and we have successfully performed the real computation, and we return it. However, if both of them didn't round to the same number, we know we'll need more precision. So in this case, a good strategy is to double the precision. And then we'll loop again until we find an answer. But as I just showed, if the working precision is greater than some maximum precision, then we weren't able to find an answer, and we need to bail because we'll keep using up memory and time until it spins out. So this real computation method will not always succeed, and that's because real computation is a very hard problem that we can't always do. Alright, so now that we have an algorithm, I can tell you that this is basically the algorithm that we use in a tool called Herbie, which is a research project I work on. And Herbie is a project which rewrites floating point expressions for lower rounding error. So Herbie takes as input some math expression, expr, and measures its accuracy on a bunch of points using this real computation method. Then it does algebraic rewrites and Taylor expansions and stuff, and picks a program which has less error and gives it back to the user. So in practice, this works very well, especially on like scientific or numeric heavy applications. So we encourage you to check it out. And yeah, interestingly, we ran into a big problem when using this algorithm in Herbie, and that is the problem of overflow. So in Herbie, we are getting expressions from the user, and we're trying to sample them and get their accuracy on input points. And so here I have an example which is slightly modified from Herbie's benchmark suite. Let's say we're trying to compute or measure the ground truth of 2 to the x over 2 to the x minus 1. And we want to perform real computation on some floating point number 2 to the 100. So as you guessed, this might overflow, and we'll see how that happens. So we're trying to do interval arithmetic and compute some real answer. And what we're going to do is substitute the numbers as before in the intervals. So we get some interval in the numerator and some intervals in the denominator. But interestingly, we're performing this on some arbitrary precision floating point number. And what may happen is that this may overflow, because 2 to the 100 is a very large number, even if you have lots of precision. And I'll get back to that point in a second. So the intervals we get will be some omega, which is some largest non-infinite number, to infinity in the numerator, and similarly for the denominator, because we rounded some big number down and rounded some big number up. Next, we can perform the subtraction, and in the denominator we'll get omega minus 1. And then performing the division, we'll get some really wide interval, 0 to infinity. And the reason we get this interval is that the 0 comes from dividing omega by infinity, and the infinity comes from dividing infinity by omega minus 1. So we got some really wide interval, even though our goal was to compute some really tight interval and get one real answer out of this thing. And the question is, like, if we bump the precision enough, would we be able to get an answer? Like, we're trying to get an answer and our strategy is to double the precision. So will that ever work? Well, I'm actually about to tell you that it will never work, and we're just wasting our time here. So I'll show you why. The rest of this talk will be specific to using MPFR, but we think the idea is generalized to using any arbitrary precision floating point library. So MPFR is a library that gives you arbitrary precision numbers, and these numbers are represented as a sign times some mantissa times 2 to some exponent. And the arbitrary precision part for MPFR is that the mantissa has some user-provided precision p, which you can set dynamically. And that's the precision that we're going to be doubling each iteration. However, unfortunately, the exponent has a globally set maximum max exponent. And this is the precision of that 2 to the exponent, right? The exponent can only have so many bits. So if we're computing 2 to the x over 2 to the x minus 1, for x is 2 to the 100, this computation actually overflows at any precision. And the reason is that depending on our exponent, 2 to the 2 to the 100 is too big because it overflows even in the exponent. And no matter how much we increase the precision, we won't be able to represent this number. And even if we could change the maximum exponent using some other library, you would still be able to find situations where, you exponentiate one more time and the number is too big to represent. So this overflow problem is going to always come up in practice, and it wastes a lot of time if we are sampling numbers and trying to compute ground truth. So our solution is movability flags. And like I said at the beginning of the talk, movability flags answer the question, could your intervals shrink at higher precisions? So imagine we have some number line with an interval on it, and the interval ranges from A to B. By shrink at higher precisions, we mean that A and B move closer together when you redo the computation at higher precision. So the idea is to track a movability flag for each endpoint separately, and this will track whether or not the endpoint can move. So the definition is as follows. When we set a movability flag for an endpoint, we call that endpoint an immovable endpoint, which means that it cannot move. So an immovable endpoint at precision p, written with this exclamation mark, proves that the endpoint remains the same for any precision q is greater than p. So if we look at our number line again and we see that A has a movability flag set, that would mean that B can move towards A, but A cannot move at all. It's exactly the same. So let's return to our example and see how movability flags might help us here. So in this example, we have 2 to the x over 2 to the x minus 1. And doing the substitution as before, we get these big intervals. And the key part is that when we do this rounding, we will be able to set the movability flag on the infinite endpoint. And the reason for that is that the overflow will happen at any p, so we'll always get an infinite endpoint on the right. The omega, however, is precision dependent, so it might get slightly bigger as we increase precision. So we only set it on the infinity. Then, now that we've learned how to set movability flags, we also need to propagate them through all of our interval computations. So here we did a subtraction, and the movability flag on the infinite endpoint stayed the same because we subtracted infinity minus 1, and that will always be infinity. Next, doing the division, we'll get an immovable 0 to an immovable infinity. And the reason for this is that this left endpoint always computes some omega divided by infinity, which will always be 0. So we have some special logic which propagates these movability flags. And at the end, we maybe did this computation at low precision, and we've proven with the movability flags that we don't need to increase the precision anymore, and we can bail early. This is just a difficult endpoint, and we won't try to do real computation on it. So that's the idea in practice. Let's see how we might implement it for a particular interval arithmetic operator. So here I have some pseudocode for the addition operator, and it takes 2 endpoints, A to B and C to D. And in normal interval arithmetic, addition is very simple. You simply round the left endpoint down, adding A and C because they're the smallest of the 2 inputs, and round the right input up, adding B and D because they're the largest of the inputs. But now, after we have computed this interval, we also want to set and propagate the movability flags. So the question we are asking is, when does this left endpoint or the right endpoint change? And really we want, when does it change when you change the precision or the inputs? So it changes when A changes, obviously. If the input changes, this will change. It changes when C changes. But crucially, it also changes if this rounding function changes. And the rounding function is precision dependent. And so we capture that with this Boolean. So we'll set the immovability flag if A was immovable, proving that it won't change at higher precision. C is immovable, proving that it also won't change. And the addition here, A plus C, is exactly computed. And we need that it was exactly computed because we need to make sure no rounding happened. Because if rounding happened, it may change as precision is increased. And so we similarly set this for the right endpoint. But we also have some special cases that I'm going to elide here. So one of these important special cases is when we have 1 to infinity. And this will result in the interval 2 to infinity, but you'll see here that the infinite endpoint is still immovable, because anything plus infinity is still an immovable infinity. This is important because if you recall from our old example, we set immovable infinities on overflow, so we want to make sure those propagate well through the computation. Right, so we've implemented all of these interval arithmetic operations in a library we call Rival, and it's available on GitHub here. All 68 operators propagate the movability flags, and it also supports the IEEE 1788 standard, which includes ill and def decorations, which basically help you determine when a domain error will happen. Also, most operators are tight, meaning that they compute the tightest possible output interval, which is an additional nice property. So you may be wondering how well movability flags work, and for that we have an evaluation on real-world benchmarks with randomly sampled input points. These are basically the problems that Herbie would run into. And the blue bars show movability flags catching this problem, and the red bar on the right shows where movability flags failed to capture the problem. And some of these problems might not actually be due to overflow. They might be just hard points. So that might be why we're not catching all of these. On the x-axis, we have the precision. So this is the number of bits at which we caught the problem. And on the y-axis, we have the number of points that were caught at that precision. So you can see that most problems are caught at 80 bits of precision, which is the lowest precision that Herbie starts with. And then as we increase precision, more precision enables better propagation of the movability flags, so we're able to catch more problems before we hit that max precision of 2,560. And if you are interested in learning more, there are proofs in the paper, and also a deployment discussion and comparison to Mathematica. There's also a longer version of the paper on arXiv, which has more details about the rest of the library and searching for good areas of the domain to sample from and stuff like that. So thanks for listening. I hope this was an interesting talk, and I'd also like to thank the Herbie team. This work wouldn't be possible without them, and yeah, thanks for listening.